Okay, so this is my analogy for the photoelectric effect. It's just an analogy for the photoelectric effect to help you kind of understand what is going on with it. Now, I like to think of the photoelectric effect as essentially a bank that does a currency exchange. Now, if at the bank you were to take in dollars and you were to get out pounds, what you're going to see there is an exchange happen. Now, the amount of money that you put in, the total value of that money, the total value here, and the total value you wind up here with any exchange, the bank is not going to give you 100% value. The bank is going to actually be charging you a fee. Now, if you had, let's say, $500 go in, and the exchange rate happened to be 1.25, meaning that if the $1.25 is equal to 1 pound, then you would expect if you put in $500 to get in 400 pounds of value, because that would be the same exchange rate. However, when you do this, instead of putting in 500 and getting 400 pounds back, they give you 380 pounds of value. They've taken 20 pounds as the fee. Now, with the photoelectric effect, this is very similar, but it is in fact different. So, if we take a look at what's happening with the photoelectric effect, you've got energy in joules here, and this is in a radiation store. A radiation store of energy. And let's assume that you've got so many joules here. The photoelectric surface is like your bank. So this is your photoelectric surface. This is like your bank. And then out, you get energy in joules or electron volts. Here, but this is going to be in a kinetic store due to the motion of the electrons. So you have a kinetic store of energy. So in this case here, you've got energy coming in, you've got energy coming out, the ability to do work. However, you've got them in two different stores, similar to dollars and pounds. The thing is about a photoelectric surface is that they don't just charge a percentage. They are a flat fee bank. And so let's pretend that this metal charges 1.2 electron volts in order to get the electron to come off the surface. So this is its fee, if you will, also known as the work function of the surface. So if we had 3 electron volts going in, charge a fee of 1.2 electron volts means that the outgoing electron will have 1.8 electron volts of energy. The 1.2 electron volts, that energy is still there. This is still totals 3 in, 3 out, except the bank has taken their fee. Now, if this was 4 electron volts coming in, a 1.2 fee is still applied because it is a flat fee, which means 2.8 electron volts would come out. If, let's say, we had 1.3 electron volts coming in, then we would have 0.1 electron volts coming out. It doesn't matter how much you got coming in, the phi is always the same in a photoelectric surface. So what happens though if I have, let's say, 0.8 electron volts coming in? Well, the phi takes up everything, and there is going to be no energy here. This will not be moving. It does not make it off the surface because it did not have enough energy coming in order for us to pay the photoelectric fee, if you will. So, if we were to think of this now in terms of the wavelength. These shorter wavelengths, which have a higher frequency, will have more energy. Right? So wavelengths, let's say, for example, if red light does not work, we go to a shorter wavelength, higher frequency. Perhaps a violet will have enough energy to pay the fee, that work function, in order to eject an electron, to get a kinetic energy store within the motion of that electron out. And if violet doesn't work, perhaps UV light will, or maybe X-rays or gamma rays. It depends on the particular metal, the particular surface, as to how much they're going to charge in terms of this energy fee, and everything comes out at the end. Hope this helps. Thank you.